Bismillahirrahmanirrahim. Assalamu alaikum. Bismillahirrahmanirrahim. Assalamu alaikum. Assalamu alaikum. Are you hearing me? Can you see the screen?
Yes, sir.
Now my request is, now सुन लें गौर से, आप अपना नाम और रोल नंबर लिख के चैट बॉक्स में एंटर करें, चैट बॉक्स में लिखकर टाइप करके एंटर कर दें, तो उससे आपकी हाजिरी लग जाएगी. Please enter your name in the chat box. Just give me a message to me in chat box. Open the chat box, write in the box your name and enter. So this will be a message that you are present. Name, roll number. Please write your name and roll number in your chat box. You know there is a chat icon in your chat box. Write your roll number, name, and then just press the enter key. So this will come on my chat. It will get recorded. It will get recorded because while lecture I cannot take attendance of everybody. So when anybody comes, he or she should write their name in the chat box with roll number and press enter key. So your name will be recorded in the chat box, and this chat box I will share. Please mute your mic, else I will mute you all. Then I will not be able to listen to you if any problem. Better you mute your mic and unmute it only when you want to talk to me with my permission. Okay? Without teacher's permission, nobody will talk, nobody will unmute. Until now, only 9 persons are admitted. Now, there are 12 participants in the meeting, including me. That means 11 students are present here. So now I will start lecture, and for that you will first confirm that you can see my screen. I'm sharing a screen. My lecture is online. It will be visible to you, that document which I will share with you on the screen. So now I have shared one PDF document. This is definition of volumetric efficiency of reciprocating compressor. Can you see it? I want yes. Huh? I want yes or no. Can you see on the screen?
No, sir.
My lecture definition of volumetric efficiency.
Yes, sir.
Yes, sir.
No, sir.
Yes, sir.
No, sir. Yes, sir.
Okay, mostly they are saying yes, sir, and one voice is coming, no, sir. I think this is joking, and I hate this person who is joking with me online. Yesterday also somebody was doing this naughty thing. Everybody was saying yes, yes. He was saying no, no. This is very rubbish thing, rubbish attitude. Behave yourself.
boy.
If you have a real problem, then talk to me. Otherwise, mute your mics, please. So let me start.
Yes, sir.
So yesterday we have derived work of a reciprocating compressor with clearance, and you will because of clearance there is effect on volumetric efficiency. Actual inducted volume is much less than the swept volume. Swept volume is just movement of the piston from top dead center to bottom dead center, and between top dead center and cylinder head there is a trapped gas with high pressure. Just after the discharge valve is shut off, so and piston moves toward bottom dead center, suction valve opens, but suction valve will not open unless internal gas trap between the piston and the head will not expand to a certain limit. When it expands like that, internal pressure is equal to atmospheric pressure, then suction valve will open and induction will take place. Fresh intake of air will take place. So because of that, we define volumetric efficiency, how much efficient volumetrically a compressor is. So this is defined by in words in two ways like this. In eta V is the symbol. It is equal to the mass of the gas delivered divided by the mass of the gas which would fill the swept volume at the free air conditions of pressure and temperature. Other definition is eta V, that is volumetric efficiency, is the volume of the gas delivered measured at the free air pressure and temperature divided by the swept volume of the cylinder. These are equations 12 and equation 14 written here in form of a definition. So this is definition of volumetric efficiency. Here you can see FAD, definition of FAD, free air delivery. What is free air delivery? It is the rate of volume flow rate of delivered, measured at surrounding temperature and pressure, which is intake pressure. If M is the mass delivered and PVT are the pressure, volume, and temperatures are atmospheric conditions, so mass flow rate M dot is equal to PV is equal to MRT, mass delivered. If it is rate, then M dot. If it is just mass, then is M is equal to PV RT. Now, here is ideal gas. That's why ideal gas law. With the help of this law, you can calculate M is equal to PV upon RT because PV is equal to MRT. If M is the mass to fill the swept volume at atmospheric conditions, then we denoted M equal to MS is equal to PVS divided by RT. This is for the mass filled in by the swept volume. But actual pressure temperature conditions in induction stroke may be different from atmospheric conditions. Actual conditions may be different because of warming up of the cylinder inside after working, and temperature will rise and pressure will be different. Now then, by definition of volumetric efficiency, 1214 above, equation 1214, eta efficiency is equal to M upon MS. M is the actual mass taken, inducted in the cylinder. MS is the mass inducted by the swept stroke, full stroke of the sweeping. That's the MS, M upon MS. So this will be equal to PV upon RT multiplied by RT upon PVS, where S denotes swept volume at the atmospheric conditions. Now from here, PV RT is common, so the result is P is also common. The result is V upon VS. So M upon MS is equal to V upon VS. So this is definition of volumetric efficiency of a reciprocating compressor. It may be ratio of the mass, induction mass divided by circ mass, or induction volume divided by circ volume, M upon Ms or V upon Vs. Let's go ahead. This diagram you will see how to calculate volumetric efficiency from indicator diagram. PV diagram is also called indicator diagram, but it is the pressure volume status. It is the pressure volume status inside the cylinder. P is the pressure exerted on the piston, and V is the volume of the gas inside the cylinder behind the piston. So you can see complete cycle with clearance volume is shown. This is the clearance volume over here. Wait a minute, I'm choosing hand eye, this one. So this is the clearance volume, VC, and VD is the VD is from here to here. This is called displacement volume. This is called induction volume, and Vs is the circ volume from top dead center to bottom dead center. Process AB. First, let us take process from A to A, from P1 to A. So this is process induction. D to A is induction process, and A to B is the compression process. It follows P raised to N is equal to constant polytropic process. Now B to C is constant temperature and constant pressure discharge. Discharge temperature is T2. It can calculate it with the formula PV is equal to MRT. So here process CD is the expansion process of the trapped gases inside the clearance volume after top dead center, and this is also follows the same law. PV raised to N is equal to constant. Because of this expansion, actual intake volume is this one, D to A, not from here to here, but it's from D to A. So you can see that this VA minus VD, this is the volume which is inducted. Now, this Vs is the circ volume. So ratio of this volume AD divided by Vs is called volumetric efficiency. Now, under these conditions, volume induced, as I've told you, is written here in this equation. VA minus VD is equal to Vs minus Vc minus Vd. Now, Vd upon Vc is equal to P2 upon P1 raised to 1 upon N, because this is polytropic process. So V2 upon V1 is equal to P2 upon P1 raised to 1 upon N. So actually V2 is Vd and Vc is the V1. So V2 upon, because process starts from D to C, proceeds from D to C. So Vd upon Vc is equal to P2 upon P1 raised to 1 upon N. From here we can calculate Vd is equal to Vc multiplied by P2 upon P1 raised to 1 upon N. This is important relation because we usually know in the problem what is Vd. We don't know what is Vd. We know Vc clearance. Vc clearance volume is given by the manufacturer. P2 upon P1 pressure ratio is also what is required by you, and N is the polytropic index. It is usually 1.3, 1.4 for air, and for any other gas that is 1.3 to 1.33. So here we are talking about air. So N is equal to 1.3, polytropic index 1.3. 1.4 is in case of isometric process. Now it will be given the problem. N should be given the problem. Now here we can readjust this in this form, Vs minus Vc, because this Vc is common in these two terms. So these two terms can be made one in this bracket, P2 upon P1 raised to 1 upon N is minus 1. So now this is the derivation of volumetric efficiency in front of you. And by definition, Va minus Vd divided by Vs is the volumetric efficiency. And this has been calculated above in terms of pressure ratios. So this is the numerator, and this is denominator. After algebraic manipulation of this equation, you can see that volumetric efficiency is equal to 1 minus Vc upon Vs in bracket P2 upon P1, 1 upon N minus 1. So we need only Vc, we need Vs, and this ratio, pressure ratio, and N to calculate volumetric efficiency. This you will learn how to do it in numerical problem. Now, what is actual FAD, free air delivery per cycle for actual conditions? Actual conditions are intake conditions P1, T1, and induction stroke. So an actual induction condition inside the cylinder may be other than the atmospheric condition. Atmospheric conditions are shown here only simple PT without subscript 1. So with subscript 1, these are actual conditions inside the induction stroke inside the cylinder. Therefore, FAD may be calculated as follows. So PV upon RT, this is for atmospheric conditions, is equal to P1 VA minus VD divided by RT1 because V is equal to VA minus VD. So P is equal to P1 inside and T is equal to T1. So these are proportional. So this relation mass inside cylinder is this condition. For atmospheric condition, this is the formula. Now FAD per cycle will be written from this equation as given above. So that is V dot is equal to VA minus VD T upon T1 multiplied by P1 upon P, where P1 and T1 are actual pressure and temperature inside the cylinder during suction stroke, and T and P are the atmospheric conditions. Now P1, T1 suction conditions given here. Then you can see there is a problem solved, which is example over here. And this is example 12.5, and all data is given, solution is given, diagram is given. So the purpose of this lecture is how to derive relation with the help of this derivation, how to solve the problems. So this is the end of this document. Now let me share with you another document. Next one, number 5. So this lecture is about multi-stage compression and optimal pressure ratio. This is an important topic because for high pressure ratios, we have to go for 2-stage, 3-stage. This is called as more than 1 stage compression is called multi-stage compression, because in one compression, excuse me, somebody calling. Hello? Hello, who is there? Hello, who is there? वालेकुम सलाम, कौन है भाई? यार जल्दी करो, मेरी क्लास हो रही है। अच्छा ठीक है, फिर बात कर लेंगे। अच्छा ठीक है, खैरियत है? मैं करूंगा कॉल।
सर कौन था?
सॉरी, मेरी प्राइवेट कॉल। So hello, disadvantage of single stage compression with high pressure ratio. Now, high pressure ratio causes high delivery temperature of air. So when we have too much P2 upon P1, discharge pressure is very high, then we can't, we should not compress it in one stage, because cylinder will be very big, motor will be very big, all design will be very heavy, so machine will be huge and powerful, and it will be very expensive and difficult to move, difficult to manufacture, difficult to run. So that is why we go for 2-stage compression. 2-stage compression or 3-stage compression. So every stage will compress from equally from P2 upon P1. Total P2 upon P1 can be divided into equal number of stages, and next cylinder will have less volume, and further next cylinder will have lesser volume, because pressure is increases continuously from discharge of one cylinder to another. So high pressure ratio causes high delivery temperature. These are the drawbacks of high pressure ratios, and these are the reasons why we should go for 2-stage or 3-stage compression design. High temperature of air during the compression process causes internal and external irreversibility, causing loss of efficiency of process. From the defining equation of volumetric efficiency, it is clear that with increase in pressure ratio, volumetric efficiency decreases. At high delivery pressure and temperature, expansion volume of clearance volume air increases, now causing decrease in FAD during suction stroke. Now, how to design multi-stage compression of high pressure ratio. So high pressure ratio, we go for multi-stage. In order to alleviate disadvantages of single stage compressor, following is the solution. Number one, carry out compression process in 2 or more stages, keep equal pressure ratios in each stage, and provide intercooling between 2 stages and after cooling after delivery. Under ideal cooling conditions, the gas will enter second stage at the same temperature at which it entered first stage. This will particularly ensure sorry. So I was here. This will practically ensure that isothermal process through multi-stage in figure will be given below. Figures 12, 15, 12, 16. Now, delivery process from first are LP stage. LP stage means low pressure stage, and induction process of second are HP stage. That means high pressure stage are at the same pressure. In figure 12, 13, total power input is equal to sum of power input to each stage. So if there are 2 stages, power input in one stage plus power input to other stage, this is the total power input to the compressor. So we have to calculate separately and then sum up. But there is a formula where we don't need calculate separately, because we should know only pressure ratio in each stage and number of stages, and we can calculate in one go the total pressure required. Now the total, sorry. Now the cylinder volumes are reduced proportionately as pressure increases in high stages. So delivery process from first or low pressure stage and induction process of second or high pressure stages are the same pressure. Whatever delivers first stage, it is input for the second stage. So delivery, discharge is called delivery and intake is called induction. Now, total power input is equal to sum of the power input to each stage. Total power of 2-stage compression is given by equation 1219 below. And next, for minimum work input, this is the important point. Minimum work input, this will prove mathematically by derivation formula for pressure ratio, optimal pressure ratio for minimal work. The pressure ratio required for minimum work input is called optimum pressure ratio. For minimum work input, keep pressure ratio in each stage same and ensure that intercooling is complete. Intercooling is complete means discharge stage 1 to 2, T1 to T2, then T2 again come to Ti, and Ti again will go to Ti should be equal to T2 must be equal to T1 again after cooling. Now, for minimum power, number of stages Z multiplied by power required by one stage. This will be the formula 1222. We will derive it. Now, pressure ratio for each stage for minimum work is given by equation 1222, which we will derive. Now, applying energy balance later on, and this is one method with the help of indicator diagram, derive the things. Another method is first law of thermodynamics, which you have studied in Thermo 1. That is called steady flow energy equation. We will apply on 2 stages, and the same formula of work can be calculated with the help of thermodynamics 1, with the help of steady flow energy equation. And these are equation 1224, 1225, 1226, which we will derive later. Now, list of equations is given first for your convenience, because this is summary of all method of reciprocating compressor design, multi-stage compressor design. You will use this equation 1219. Total power of 2-stage compressor is N upon N minus 1 M dot RT1 P1 upon PI. This is PI, that is intermediate pressure, and ratio N minus 1 upon N upon N minus 1 upon N minus 1 plus P2 upon PI, raised to n minus 1 upon n minus 1. So this is for one compressor, this is other compressor. So 2 compressor power added, this we will derive. Now, this is the optimal condition, which we will prove mathematically later on. Here is given only list of equations. This is equation 1220. This says that intermediate pressure between two stages from if P1 is the initial pressure, P2 is the discharge pressure, final delivery pressure, then what should be intermediate pressure if you want to divide this in two equal stages? For that purpose, Pi square must be equal to P1 into P2, that is Pi intermediate pressure must be equal to under root P1 multiplied by P2. This is equation 1220. Now equation 1222 says about total minimum power. If Z number of stages, here Z, if 2 stages, Z will be 2. If 3 stages, in 3 cylinders, then Z will be 3. 4 stages, 4 cylinders, then Z will be 4. So Z is number of stages multiplied by this formula for one compressor. This is the formula of work for one compressor multiplied by Z number of stages over here. And here, n upon n minus 1 divided by Zn. This one. This is the only change. Only with the help of this formula, you can calculate total work of multi-stage compressor if you know the single ratio P2 upon P1, compression ratio. Then we will have equation 1223, which shows in multi-stage compression how to divide pressure ratio. Total pressure ratio is P2 upon P1 in multi-stage compressor. So if Z is number of stages, then P2 upon P1 must be equal to 1 upon, pressure ratio for each stage must be equal to P2 upon P1 raised to 1 upon Z, where Z is number of stages. Now, as I've told you, from thermodynamics point of view, we have derived this relation before previous lectures. In low pressure, heat rejected. No, we will derive in later on equation 1224 by applying first law of thermodynamics that work in low stage minus mCp T I minus T1. This will be heat rejected in LP. So low pressure cylinder. This is required to design the intercooler because how much heat to be is given to the intercooler depends on this quantity. Then heat rejected in intercooler must be equal to, with the help of this equation 1225, m dot Cp Ti minus T1. So these equations will help to design complete, this is thermal design of complete compressor. Remember, we are studying thermal design only in thermodynamics. We don't study mechanical design. Mechanical design is studied in theory of machines or machine design, where you do stress analysis and strength of material, things like that. Now here we do only these work input, temperatures, pressures, and heat rejected. So heat rejected in high pressure stage is equal to W dot H minus mCp T2 minus T1. This is crucial. Question 1226, we need it for design. Now again, I will show you all the figures involved here. This is first stage cylinder, LP cylinder. This is HP cylinder. To the left side is LP cylinder. Right side is the HP cylinder. There's my tool is missing. I'll change my tool. You can see that there is a heat exchanger over here. Heat exchanger is a multi tubes with shell, and from one side, cooling water is entering, from other side, cooling water is getting out, and in between, in the tubes, water is circulating. In between, hot air, compressed air is circulating, and air gets cooled from T1. Its temperature remains same, whatever is. So with little time is left, very soon we will finish this lecture. So whatever is the discharge temperature, the same will be intake temperature of the second cylinder, and this is the purpose of this intercooler. So this is called complete intercooling when intermediate temperature is equal to T1, and T2 can be calculated with formula later on. So this is the process shown in two-stage compression with intercooling. You can see that this is T1, this is T2. See the coordinates. T is the temperature, y-axis, and here it is entropy, TS diagram. So on TS diagram, constant pressure line, isobaric lines look like this. So this is P1, this is PI, this is P2. From P1 to P2, polytropic process pressure compression is done from T1 to T2. Temperatures increase, but at constant pressure PI in intercooler, it is cooled down again to T1. Then in second stage compressor, compression takes place from PI to P2 and temperature rises from T1 to T2 again. In after cooler, again, we can cool it down, bring it to T1. So this is called as complete cooling. So after this, we will continue and let us finish lecture here. So next lecture will be inshallah next week, Tuesday at 11:15. Hope you will be present in time. Any questions? If you have any questions, please. नाम बताएं और कोई सवाल करें जल्दी से, वक्त खत्म होने वाला।
सर ये स्लाइड हम कर देंगे।
हाँ, इस स्लाइड में आपको डिस्पैच कर दूंगा बाय ईमेल। मेरे ईमेल चेक किया करें, कोई व्हाट्सएप में नहीं हो गई।
ठीक है सर।
ओके सर।
स्लाइड में शेयर करो।
सर व्हाट्सएप करना है।
मैं नहीं, व्हाट्सएप में नहीं करूंगा, मैंने कह दिया है। मैं जो कहा वो करो, अपनी मर्जी मुझ में मत चलाओ। मेरी मर्जी मेरी मर्जी है कि ईमेल देखो, दैट इज इट। और दूसरा ये है कि वो जो है ड्राइव है, गूगल ड्राइव है मेरी, उसको मैंने मखसूस कर दिया है कि मैं जो वीडियो इस अभी कभी लेक्चर भी, पिछले 2 लेक्चर में ऑलरेडी वीडियो कर चुका हूँ, तो वीडियो भी शेयर कर देता हूँ। और वहां से आप जिसको दोबारा सुनना है घर में बैठ के ऑफलाइन डाउनलोड करके देख ले, जितनी मर्जी इच्छा है उसको लेक्चर को देख के समझ में नहीं आता बार बार देख। ठीक है, ओके जी।
पेपर ऑनलाइन होंगे।
लेट अस एंड द मीटिंग। क्या करें?
ओके बाय बाय।
क्या सवाल है, बोलो क्या सवाल है आप? मैं मीटिंग खत्म करने वाला हूँ, सवाल करो।
सर पेपर ऑनलाइन होंगे।
क्या चीज?
सर थर्ड सेमेस्टर का रिजल्ट कब आएगा?
ये फजूल बात नहीं कर। रिजल्ट कैसे है? रिजल्ट क्यों आएगा? रिजल्ट जो है ना यूनिवर्सिटी बनाती है, रिजल्ट एग्जामिनेशन डिपार्टमेंट बनाता है, टीचर खाली अपलोड करता है और बाकी काम जो है ना वो एग्जामिनेशन डिपार्टमेंट करता है। इसके लिए आप कांटेक्ट करें वो क्या है, सिद्दीक साहब। सिद्दीक साहब हमारे एग्जामिनेशन के इंचार्ज हैं, वो बताएंगे आप, या रोजीना को कहें, रोजीना जो है ना सिद्दीक साहब से बात करके वो आपको बताएंगे। एनी अदर क्वेश्चन?
सर पेपर ऑनलाइन होंगे।